Hi everyone, and today I'm going to show how to build a USB speaker USB sound card based on the STM32 microcontroller board. So here I have STM32F4 Discovery Board, which is connected to my computer through micro USB, and I also have a headphone which is connected to the audio jack of the microcontroller board, and my computer detects the the microcontroller board as audio device. So we can play some music. This is one of my favorite songs. And this music is produced on the headphone. And the audio quality is pretty good. It is really cool project because you will design an actual device. Also, you have full access to the audio data within the microcontroller, so you can do filtering, you can extract some information from the audio data, or you can trigger the microcontroller to do certain actions. So this project could be a gateway to many other interesting projects, and you will learn a lot. So enough words. Let's move on and let's talk about the hardware I'm using. So in this project, all we need is this board, STM32F4 Discovery Board. So it has this micro USB, so we can design our own USB device based on the STM32 microcontroller. Also, we have this tiny digital to analog converter, specially designed for audio applications, so we can stream data to this chip, and we can produce high quality sound using this audio jack. So for this project we have everything, and I think it's a good investment to buy this board. After a brief introduction of the hardware, it's time to talk about the firmware. And traditionally, I will use STM32 Cube IDE to develop my projects. And what we have to do, of course, we have to create a new project for this particular board. And once you do it, we will end up with this device configuration tool, or let's say CubeMix file. And what we have to do first is to configure peripherals related to DAC, digital to analog converter. So here, among these categories, we just need to press multimedia, and here you would find peripheral called I2S. So I2S is not I2C. I2S is a peripheral, is a protocol specially designed for streaming audio data. So here we have to choose half duplex master mode, so the microcontroller will be in master mode. Also, we have to enable master clock output, and we have some parameters here to configure. So the sampling frequency, selected audio frequency, would be 48 kilohertz, and we have a 16-bit resolution, so we have pretty high audio quality, I would say. And we are, of course, transmitting audio data to the audio codec. And also we have to enable the interrupts, and we have to enable the DMA in circular mode. Since we are working with audio application, it is time critical, therefore it is essential to enable DMA. And if you don't know DMA what it is, you can refer to my another video on my channel where I explain the main principles of DMA direct memory access. And also you might ask why I'm using I2S3, not I2S2, because if we open the schematic of this board, you can find the link to this document on the description below. So as you see, we have this digital to analog converter, let's say audio codec, and as you see, we have these pins to send audio data. Okay, so as you see, it's written I2S3. That's why I have to use I2S3. And as you see, we have master clock. That's why I just enabled master clock by ticking this box. So once we start streaming audio data through these lines, we have a headphone connected here. So it will generate corresponding audio signals. However, I want to point out that before streaming audio, we have to enable the audio codec. We have to define the data format, the frequency, and other things. And to do that, we have to use I2C protocol. I2C protocol. And here we have the pins for that. And we have this address, I2C address. So to do that on my project, inside of connectivity, I use I2C1, and here we just need to enable by choosing I2C, and the rest I think is just a default idle values. And if we check the GPIO settings, as you see, we have PB6 and PB9, and if I check the document, we have exactly the same pins. It means that we have to use I2C1. And also, as you see, we have this reset pin connected PD4. So on my project, let me show this pin. It's just over here. On my project, I have this PD4 and I configured this pin as GPIO output, and I put this label for that. So we will use this pin later to reset the audio codec, the digital to analog converter. Before moving further, I also want to point out that when we define the frequency for I2S, so let me open parameter settings. Let me open it wider. So as you see, we chose a frequency of 48 kilohertz, but in reality, the frequency is 47.991. So it is difficult or even impossible to get exactly 48 kilohertz. If we get something close, that's enough. And to get something close to 48 kilohertz, you just need to play with these parameters. So eventually we have this I2S clock frequency which will drive the I2S peripheral. So by tuning these values, eventually you have to get something very close to 48 kilohertz. So you can just use exactly the same values as I use here. Hope I covered everything related to the audio codec. Yeah, I think that's it. Once we configure I2S, we have to enable USB, of course. So inside of connectivity, we choose USB full speed, and we just need to choose a device only, because the computer will be host and our microcontroller will be device. That's why we choose device only, and the rest of the parameters, I think we keep everything by default. So we keep the default parameters. However, I want to point out that USB protocol is very complex. So ideally, we have to develop our own stack, our own library, but it's a tedious and time-consuming work. Therefore, we will use a library provided by STM Microelectronics. So if you press this middleware and software packs, you need to find this USB device. So once we press it, we just choose audio device class. So we can, for example, design mass storage class, or we can design human interface device, for example, mouse or keyboard. But in our case, of course, we have to choose audio device class. Then we have these parameters. Everything we keep by default, except maybe you need to change the frequency. So this our audio frequency has to be 48 kilohertz. So once we do it, it will generate files and libraries. So we don't need to bother about the USB protocol. So all the libraries generated will handle all the events, everything related to the USB. However, if you want to learn USB in a more rigorous way, in a more detail, I can recommend this course where you would learn how to design human interface device based on the STM32 microcontroller. And I want to say that it's not an advertisement. I don't get paid for it, and also I don't know that a tutor personally, so it is my personal recommendation, that, like, recommending the best for you. Okay, once we do that, we almost over. The final thing I want to say is that we have to use one of the timers to create timer update interrupt. So if you don't know what it is, you can again refer to my another video on my YouTube channel. And so here I'm just using this timer to create timer update interrupt every 2 milliseconds. Okay, so nothing new here. So we finished configuring all the peripherals, so we can save the file to generate the code. To do that, you can press Ctrl S, or you can press this button, device configuration tool code generation. The code generation is over, so we can start coding. And the first thing we have to do is to make sure that the stereo DAC works properly. So to do that, first let's check the schematic of the board, and we can get here the serial name, the name of the stereo DAC. So it has this name, CS43L22. So based on that, I could find the datasheet of this integrated circuit. So here what I want to say is that we have these registers: clock control, interface control, let's say interface control 2, pass-through select, and other registers that allow us to configure the integrated circuit. Then we can start streaming our audio data. As in other cases, we have to write specific values to the registers, and once we do it, the stereo DAC is ready to receive our audio data. So in our code, to make everything organized, I created separate source and header file, as you see here. So we have the address, the I2C address, and also I defined macros for reset pin number and the GPIO port. And instead of using this I2C1, I2S3, I defined these macros. So instead of using this, I can use this macro. So if something changes, for example, later if we want to use I2C2, for example, instead of 1, we can just change it here. And then we have these registers, the macros that define the registers, and we will use just a few of them. I decided just to define all of them. And then we have these prototypes of the functions that I'm going to explain right now. So let me open the source file. So the most important function, I think, is this initialization function. So what I do here is just I reset and set reset pin by having this delay. So after that, our stereo DAC is ready to function. Then here I just power off the codec. Then I choose the headphone. So the stereo DAC can drive headphone and speaker. You can see it from the schematic. So this is our audio codec. So as you see, we have headphone and speaker, but of course we will use only headphone. Then clock auto detect, and then we choose I2S mode up to 24-bit interface, and then I enable digital soft ramp emphasis filter, then emphasis filter, and I set the volume, PCM volume 0 dB, and that's it. And you can just look at these pages. I just wrote these comments to make sure that everything is clear for you. So here you just need to look at page 38 if you want to know how to power off the codec. And to choose a headphone, again, you can look at page 38 of the datasheet. In addition, we have these auxiliary functions to mute. So when muting, we just switch off the headphone and we mute them. And when unmuting, we do opposite things. We unmute headphone A, B, and we turn on the headphone. And to play the audio data, we have this function. So this is the pointer to the data and the number of samples we want to play. So when we want to play, we just unmute and we power up the stereo DAC, and we start playing. So when starting playing, we just transmit to I2C through DMA. So this is something we define here. So instead of I2C, we can so instead of this, we can actually use I2C. They're interchangeable. And when pausing, what we do, we mute, we power off, then we pause DMA after some delay. And when resuming, we do opposite things. We unmute, we power up, and we start DMA again after some pause. And we can also stop the stereo DAC as well. And we can set the volume. I never used that function, to be honest. And also, when using DMA, it is important to use the callback functions. So we have the buffer, for example. So I2S will start streaming that data to the DAC. So at some point it reaches the end of the buffer and it starts from the beginning. So to capture this event when the buffer is over, we have this callback function which is invoked automatically. Okay, this callback function when the DMA reaches the half of the buffer. And when this happens, we have these functions inside to be called. And as you see, we have this we keyword, meaning that we can define these functions in other files, and that functions will be called instead of these So it is pretty convenient when we want to integrate some custom file to libraries. And that's it, I would say. And to test how this audio codec, to test this stereo DAC, what I do first, right now we don't need USB. I can comment them. So USB and the timer for initialization. And here I just want to create a sinusoidal frequency, sinusoidal signal with 1000 Hertz. So we have the sampling frequency of 48,000, and I will create a 1 period signal. So based on that, I just define the buffer length, and based on that, I create this array. And this array has, and I multiply by 2, meaning that because we have 2 channels. And inside of the inside of a main function, I have this for loop to create my sinusoidal function. Okay, so we have this frequency which is 1000 Hertz, and once we create this signal, I just play it by calling this function. So we have buffer audio, we have the buffer length, and we multiply by 2 because we have 2 channels. And right now we don't use USB. We have to make sure that the stereo DAC works properly. So I hope I explained everything. So let me debug the code. So I'm in debug mode, and let me resume the code. And I guess you're hearing this beeping sound, high frequency sound. Meaning that our code works perfectly. And also want to mention, forget to mention that we have to initialize the stereo DAC. So everything is working well. So in the next part of the tutorial, I will explain how to get data from USB and how to produce the sound using that data. And there will be some interesting problems that we will solve together. Also, another important thing is that the source code of this project is available on GitHub as a private repository. To get access, you have to become the community member on Patreon or on my website. Once you do it, you get access to all these projects. So that's it for today. If you have any questions, feel free to ask. I wish you a happy time in this new year. See you soon.